So we've come to the end of this mini-series on the Maths Admissions Test from 2018 for Oxford, Imperial and Warwick. And we're at the last question, question 7. And as with question 6, this is just for applicants in computer science and philosophy, but good practice for the other courses as well. To some extent, just the questions will still be mathematical, but maybe we'll have something a little bit more algorithmic in their approach, something a bit more relevant for computing in particular. Please do like the videos, subscribe to the channel, and share this with anyone that you know who's applying for this paper, or who might enjoy the challenge of having a go for practice. And we will get on with question 7. So in this one it says we've got a character in a video game who's collecting magic coins attached to a cliff face. They're going to start at the bottom left corner S and must reach the top right corner E. So we've got this kind of diagram down here showing this situation. It says 1 point is scored for each coin C that's collected, and we can see there are coins dotted around here on the way, and the aim is to reach the top right corner with the highest possible score. So we just want to have collected as many coins as possible en route. And it says that each step the character can move either one cell to the right or one cell up. That's our key restriction here really, which is that we can only go up and right, we can never go left or down, otherwise we could just collect all the coins. It says at each step the character moves one right or one up, but never down or to the left. So it says let Cij equal 1 if there's a coin in position ij and Cij equals 0. Otherwise, so we're just using ordinary coordinates here, right? So I for the x coordinate, if you like, and j for the y coordinate. So if I took I equals 2 and j equals 3, that would be this square just that I'm on just here. X equals 2, y equals 3. We've just got a grid from 1, 1 all the way up to 8, 8. So that could be useful notation if you want to refer to a particular square as you go through the question. Describe how the maximum score is achievable on reaching position ij, where I is greater than or equal to 2 and j is greater than or equal to 2. How that can be determined in terms of the maximum scores ij minus 1 and I minus 1j achievable at the positions immediately below and to the left. Okay, so just make sure you understand what this is saying. If I'm at a particular cell here, and this one is, let's say this one is the one I'm currently thinking about as ij, then if I went to the left one here, I'll draw that there, but this cell would have I minus 1j, and this one would be I j minus 1. It's a bit hard to write the coordinates in here, right? So actually, really, all I have to do is think about how I go from one cell to the next. So if I let's say I was thinking about this cell here, right? The maximum score here is really just either whatever's bigger of the maximum score that I can get from here and here, because I must have come from one or the other of those positions to get to this square here. Whereas if the square is one that has a coin in it, it'll be the maximum that I could have got from here or from here, but then plus 1, because I'm now also scoring an extra coin when I achieve entry into that cell. So I could write that by saying that the maximum at cell I, j is just going to be I'm going to say the maximum of these two objects, so m at I j minus 1 and the score m that I could have achieved at I minus 1j. So this is just notation. The maximum, hopefully you've seen this before, the maximum of a comma b just returns the largest of the two of a and b. It's not just that, it's this plus Cij, okay, because remember Cij in the question is 0 when there's not a coin and 1 if there is a coin, so this deals with both cases at once, right? Both the case where there's a coin in the cell I've entered and the one that I haven't. So I just take the maximum of the left and the down move plus 1 effectively if it's got a coin in it. Okay, so that's the most efficient use of notation. You could also write that out in other ways, but I think you want to try and be as efficient with the notation as you can here. Right, now it says in part 2, it says use the result from part 1 to fill in each cell of the diagram above to show the maximum score achievable on reaching that cell. What's the maximum score achievable in the game? And there's a spare copy of the diagram at the end of the question, right? So I can just go to this diagram and start adding in the score. So obviously I can't have achieved any score to begin with, and it's fairly easy to see, right, that actually in all of these cells down here there's just no way that I can possibly have scored at this point. But as soon as I enter this cell, I could have scored 1, and now at every stage I'm going to follow my rule really and just look below and to the left, look at the maximum I could have achieved up to that point, just add 1 if there's a coin, right? So like this, so this cell here, okay, the maximum of left and down is the left one here, which is 1, so I could have got 2 by this point, and then the one to the right here, the maximum of 2 and 0 is 2, so I can just keep filling these in. In fact, you can see things like if I just go all the way up here, there is no left, so it's always just the only way I can get here is just by going directly up, so I must have 1, 1, 2, 2, 2 here, and I can just keep filling in upwards here. Now of course anywhere up here I could have had 2, still 2 is the best I could have had here or here. Again in this cell the best I can do is 2, but on entering this cell I can get a third, and then so the best I can do here is 3 and 3. If I go further down the bottom here I could get 1 at this point, so I could also have 1 in the cell above it, and I could have had 2 then entering this cell. So that means that this is also 2 still, 2, and I'm going to get a 3 here, and then entering this one I can have a 4, and then a 4 at the top here. So hopefully you can see how this goes, and we can just fill in the rest of the diagram here. I've got a 1, 1, 2 is the maximum here because of coming in from the left, 2, this one is 3, and the best I can do here is 3. I could have got 4 at this point, 4 at this point, and we can kind of see actually the best route is to kind of head up this way, because I can now get a 5 on entering this cell, but I do need to fill in the rest of the table as well. So down here I get a 2, let me just fill these in a bit more quickly, 2, 2, 2, 2, 2, then 3, 3, I could have had 4 here, the best I can do is 2, I could have got 3 at that point, so 2 and 3, that means all of these are 3s, I could have got to 4 anywhere down here, but the only way to get to 5 is to come through this route at the top. Okay, and so what is the maximum score achievable in the game? Well, the answer is 5, and now we've got also this chart that can help us see the path through there. Okay, so really just takes a second to get your head around what's going on here, but once you have, it's not too bad. Okay, so let's just take a copy of that grid so we've got it again, and in part 3 it says given the array of scores mij that we've just created, describe a method for tracing backwards from E to S a path that if followed in a forward direction by the character would achieve the maximum score, and draw one such path across the cliff. So in fact I think probably finding one such path is maybe the easier part here, and actually describing the method is perhaps slightly trickier, but you know, as we've seen a lot in this paper, really expressing yourself precisely is a big part of the challenge. Okay, but if I start at the E here and go backwards, okay, I've got to find a path that would have led us to here. So actually, if you think about it, well, okay, I must have gone from this coin to the corner. We saw that as we constructed the solution. Now, if I think about where I could have come from here, well, actually, I could have come from this 4 or from this 4. So really, either of those would be valid, but I really do have to end up back at this coin here. So let's just pick either of those routes. But you know, again, there are multiple routes through this little section here. From the 4, I've got a 3 here or here. So I could have had a 3 at this point or at this point. So again, I could take either route here. But now at this point, though, I must go down and collect this coin. But again, from this point, from this 3 here, I could now go left or down. It doesn't really matter, so I go left. Now here again, I could still actually at this point go left or down, but let's say I went down, I now must go down as far as to get this coin, so I can never, you see, take a route that takes me into a lower score here unless I'm on a space where I've just collected a coin. And that's really the rule that we're trying to find here, which easiest way to work it out is just to play around with the route, right? So I can go down to, so I get to 2 here, I can go to a 1 here because I'm, I must reduce from this point to 1. I can either reduce to 1 or 0. I've got to reduce to the 1 to collect, to make sure I've collected this coin, and then from here I can just come back down to the start. Okay, so actually, as we created that, we've also seen a kind of logic there, and I suppose the more precisely and kind of algorithmically you can express it, the better. You know, they're looking for people who can write down instructions for a computer, I suppose. But we can say it in words here. There's no need to have code or pseudocode, even if you know what that is, particularly here. So, so what am I going to say? I'm just going to say, trace to I minus 1 j or I j minus 1. Let's say whichever is, or whichever has maybe the larger value of m. Okay, so I'm always basically taking the choice of the left or down as to which one is larger. If tied, just take either route. Okay, and that will always do it. You could also explain this by saying something like keep going along a route with all the same numbers until you hit a coin, and then follow this sort of procedure. But actually, every step, that's what I'm doing. I'm always looking back and saying I've only ever made a choice here to go to the largest possible out of my left or down, and it's only in cases like this one here where I could have gone either as a tie that I have to actually make a choice. So that's what you would tell the computer to do. You would tell it to read these two values that you've worked out, pick the larger one, and then trace the path through, and just pick arbitrarily if in the case of a tie. Right, last part of the question and the last part of this paper. So with the pattern of coins shown, how many different paths from S to E achieve the maximum score? And can we describe a method for computing the number of such paths? Now, how can I do this without making a mess of my diagram? I might have to redraw something here, but there's a couple of ways of thinking about this. So firstly, answering the first part of this question is a bit easier than writing it down nicely in general. So how many different paths from S to E are there, right? Because I sort of see that some parts of this path are necessary and others were optional, right? So like this part at the end I had to do, this part at the beginning I had to do, but I did have a bit of choice, say in this region here, right? So I could actually, let's say when we were tracing back here, the first bit we realized we had some choice over this area here, right? And actually in this region here, you see I've got to basically go across this rectangle, but I've just got to choose when to go up at some point, but I could do that at any point, right? So I could go up and then across, or I could go across, up, across, or I could go all the way across and up as I did in that original one. So there's actually 3 different ways of crossing that rectangle. Similarly, I've got this square here where I actually must hit these 2 coins, right? And there's 2 ways of crossing. Two ways of crossing that square. Okay, so let me just circle the 2 and the 3 that I've got for my options. So there would be 6 ways then of getting from here to here, because 2 times 3 routes through those two sections. And then I've just got to think about how do I cross this square here, right? And in order to do that, again, right now we have to count the paths a little bit more carefully here, right? I can either go through this coin here, and once I've gone through this coin, this one here, right, I can I've got to cross this 2 by 3 rectangle. So again, there are 3 ways of doing that: either across and up, up, across, up, or all the way up and across. So that's 3. Or I go to this coin, and if I go to that one, there's actually only 1 route through. So in total, I've got 4 admissible routes through this square. So the basic answer to the first part of this question is that it's 4 times 2 times 3, which is that there are 24 routes. Okay. Now, that's fine for this particular pattern of coins. I can just show that, and you might be able to describe a method like this in a slightly more general way. But you can envisage different patterns here where you might just run into difficulty with this particular argument. Especially if it would also have been viable to go around here and here. If you've got quite large blocks that you could traverse where there are lots of different routes, whereas here there's lots of coins you really do have to collect, and only 2 actually that are optional. So how would I describe that in general? And one way would be to kind of start creating an entire grid counting the number of routes up to each point. Okay, so I can say how many ways are there to get to any of these valid paths, and I think in order to do that I'm going to need another copy of the grid. So let's just add that one in here. Okay, so my general answer would be to say, okay, put these side by side and say how many ways are there to get to each point. So at the bottom here, and I only really have to consider routes obviously that are going to be sensible ones that lead us towards the end here. So there's only 1 way to start, and again there's only 1 way to get here, only 1 way to get here, and I must get to this point, so there's only 1 way here. Similarly then there's only 1 way to get here or here through admissible paths. Remember there's no admissible paths that go through this kind of region underneath here. Again there's only 1 way to go up here as we saw, but then if I think about these ones, then okay, so actually there's still I guess only one allowed way of getting here, but there'd be 2 allowed ways of getting here. Remember I can't cross from this cell to this cell, which is why this is still a 1, but I could come across like this or like this, so I get 2 at this point. And this cell I could have come from this way or this way, so I get a 2. And then that means that at this point here I've got 2 ways to get to this one and 2 ways from here, so that's a 4, right? So we start building this up, right? So there's 4 ways to get here, then there's only 1 way now to get to this one or to this one, but when you're looking at this cell there's all these admissible routes that come either through here or through here, so I'd have to add the 4 and the 4 to get 8, and then again only 1 way from there to get to either of these cells, but then actually 16 in total to get to this one, still 8 ways to get to this one from here, and then 16 plus 8 to get into this one, 24, and that also traces me all the way to 24, right? So I think this describes a more general method where we describe something like working through the grid from S, okay, and we just describe this process. So we say, so we essentially sum the so we're going to sum the number of admissible paths from below and from the left at each square, and then continue until we get to E, okay, and if you've kind of accompanied that with this sort of diagram, I think with the example with the numbers for the particular example they're looking at here, I think that'd be a very clear answer. I think in a real exam I'd be looking to write a bit more than this, and to again express that as precisely as you can. It's something close to what an algorithm might implement, right? And that's what I'm trying to say here. Start at S at each stage, look below to the left, add the number of admissible paths there are together, but only if it is admissible to come from that. I suppose that's the actual meaning. Only if it is admissible to come from that square, right? So, for example, this one here, I didn't just add the 1 and the 1 because this was not this was not an allowed route. Okay, I couldn't come across here. So you actually might need to say that moderately more precisely than I've written it down here, but something along those lines, and you will get all of the marks. Okay, so I'm going to finish the series here for this map paper. I hope it's been useful. Remember, the whole paper is there in a playlist, and I've also done some questions from 2016 and 2017, the short answer questions mostly, plus a couple of the longer answer questions. They're also in playlists that I'll link below. Please don't forget to subscribe, to like the video, and to send this to any friends you know who are taking the paper. And I will be back at some point in the future with another series, perhaps looking at some step questions, maybe some other topics. We'll see. Please feel free to give me some suggestions below, and I will do my best to help you out.